For Lab 4, we analyzed the current and potential difference throughout a circuit with different elements such as capacitors and bulbs. We used the Online Circuit Construction Kit, or CCK, from the Colorado PHET project. Major physics principles we used in the lab were Kirchhoff's laws, such as the loop rule and the node rule. We used these in order to calculate potential difference, current, and resistance around a circuit. This is the first circuit that we analyzed. The picture on the left is how it was represented in the lab instructions, while on the right is how it looked once I created it in the CCK. I predicted the currents I1 and I2 to be equal because the current does not split anywhere and therefore should be the same going around the loop. The way I got 0.02 amps is the loop rule. The potential difference of the batteries, or EMF, minus IR, which is the voltage drop across the resistors, is equal to 0. Since the resistors are in series, you can add the resistance of them to create an equivalent resistor and then solve for I. These predictions were correct once tested in the CCK per the ammeter's recording. When reversing the ammeter, the recording stayed the same because the sign of the current only indicates the direction, and the ammeter here is measuring the magnitude of the current. Note here that the ammeter in the CCK only displays the current to two significant figures. If you replace an ammeter with a voltmeter, which in this case meant to connect the circuit with the 2 voltmeter probes, the current goes to 0 as indicated on the other ammeter. The potential difference of the voltmeter is -3, since the loop rule is still the rule to use. The voltmeter has extremely high resistance, so the voltage drop across the voltmeter is all of the voltage gained from the batteries. The reason that the ammeter does not affect the circuit is that it has 0 resistance. In real life, it probably has a small amount of resistance, so it may alter the circuit a bit. If you were doing this in real life and not through the ideal simulation, the ammeter would cause the current running through the circuit to decrease since it would add resistance to Req, since it is also in series, which was used earlier to solve for the current when I equaled Req over EMF. Our next task was to measure delta V around the newly closed circuit. Across the two batteries, the potential difference was positive 3 volts due to the EMF of them. Across the resistors, the voltage drop was proportional to their resistance since delta V is current times resistance. Anywhere else along the wire, the voltage drop was 0 volts because the wire in the simulation has 0 resistance, so delta V is current times 0, which is 0. The current was still recorded as 0.02 amps. We know that these are accurate values due to the loop rule, since 3 minus 0.96 minus 2.04 indeed equals 0. In this graph, you can see how the voltage goes up across the batteries, then down across the resistors, and then back to 0 throughout the loop. Next, I calculated the resistance using the values of delta V and current that I recorded from the simulation. The reason that the resistance was off is because the ammeter's recorded current was 0.02 amps, with few significant figures, as noted earlier. In reality, the current is 0.0204086. This will alter the calculations enough to change the resistance by a small factor. In the next circuit, we have a bulb with a resistance of 10 ohms and a capacitor with capacitance of 0.2 farads. The battery is 9 volts. When connected, the light produced by the bulb shines bright and then decreases, which happens when the capacitor is charging. The current stops once the capacitor is fully charged. When the battery is removed, the light bulb shines bright again and then also dims off. This is because, in this case, the capacitor is discharging. The time for a capacitor to charge increased with the bulb with higher resistance when the 10 ohm bulb was replaced by a 20 ohm bulb. This is because the time for a capacitor to charge and discharge in the circuit with a resistor, also known as a RC circuit, is related to something called the time constant, represented as tau, or RC. If the resistance is lower, it takes less time for the capacitor to charge. If you charge the capacitor with a battery in the CCK, it charges instantly. You can relate this to the RC time constant. Since R equals 0 in the ideal model with no resistors or bulbs, it should take 0 seconds for the capacitor to charge. In real life, wires themselves have some resistance, even if small, so the capacitor would then take some time to charge. For the last part of the lab, we found the RC time constant by discharging a capacitor and graphing ln delta V over V naught versus time, which gives a straight line plot. As you can see, this is what the graph looks like, and the slope is the RC constant, which in this case is 0.1325. The calculated value of RC, which is just resistance versus times capacitance, was 0.15, so you can see that these two values agree since they are very close. In conclusion, the CCK was a good and helpful model to learn about current and resistance. It is just very important to think about the real-life situations as well while using the ideal tools that are in the simulation.